Welcome to another video on my channel. Now this video was actually requested by one of my subscribers who commented asking for a full in-depth overview of limits through graphs. So this is what this video is about, and this is taking a bit more of a visual approach to calculus. So let's dive right in. There are a few reasons why one would even use graphs for limits in the first place. The first is a visual understanding of abstract concepts. Basically, limits are not always easy to understand, and they can be quite confusing, often taking a lot of algebraic manipulation and a very solid understanding of algebra. The second benefit is you can quickly identify function behavior or how a function moves. Number 3 is you can see patterns that algebra might miss, where let's say something is going in a spiral path, but a complex trigonometric equation might not always show that. And it also builds a sense of intuition for further calculus concepts, and intuition is always very good, pretty much about as good as practice, so you start to understand the underlying concepts behind all these. Just a quick review of two-side limits. First, we have to find the left-hand limit, then we have to find the right-hand limit. Then we need to compare the results. If it's the same value, the limit exists. If it's the different value, the limit does not exist. Three main types of discontinuity. Removable, where basically you have a hole in the graph, which I'm going to show a jump where there's sudden breaks, like one value it's this point, but then the same x value at a different y point. And infinite is if we have vertical asymptotes. So that's basically about it for all the discontinuities, and in the next 3 slides, we're just going to quickly go over each of them in a bit more detail. Removable discontinuities is if we have an open circle, or what we like to call hole in the graph. This limit exists, but the function is not defined at that point, and it could be fixed by filling in the missing point, and it would just be a regular continuous function. Jump discontinuity means the graph jumps from one level to another, basically like some piecewises. Let's say I have x as y is equal to x as x is less than 0. That means at 0 there would be an open hole at 0. But if we say y is equal to 1 for x is greater than 0, at that same value 0, you would basically have x is equal to 1, and that's kind of like a jump because no x value can have two y values. And the left and right hand side limit exist, but they're different, so no two-sided limit exists at all. The last type of discontinuity is infinite discontinuity, where the function approaches plus minus infinity at certain points. It creates vertical asymptotes, and it's what people like to call the most dramatic visual pattern, as there's asymptotes, and if you zoom in, it's going to show very small differences from 0, similar to the graph of y is equal to 1 over x. Here is the first example, and as I said, we're gonna be plugging this in and using graphs to figure it out. So we're given f of x is equal to 10 for x is less than 5, and f of x is equal to 15 for x is more than 5. If we switch over to Desmos and we open up the graphing calculator, what we have here is f of x is equal to, if x is less than 5, or instead of f of x, we need to do y is equal to 10 for x is less than 5, and y is equal to 15 for x is greater than or equal to 5. So if we look at it over here, this means we have one from the left hand side and one from the right hand side, and let's evaluate it. So if we approach the limit from the left, so if we start at like 8, then we're like, okay, it's 15, we go closer and closer, Maybe we even zoom in on the graph. Now, okay, 5.007006, all the way until almost 5, and you can see it's approaching 15. Now, if we zoom in and look on the other one, we can find that if we're approaching from the left, if we have 5 over here, 4.85, then if we go more and more and more, we can go to 4.999, and as you can see, it's still approaching 10. So what it's doing is from the left-hand side, it's approaching 10, and from the right-hand side, it's approaching 15. But these two limits aren't the same, and this is what we would call a jump discontinuity. So the limit does not exist. And over here is all of the answers. If we have it from the left, it's equal to 10. If we have it from the right, it's equal to 5. But since the two one-sided limits are not the same, the two-sided limit does not exist. Here is another discontinuity called the removal discontinuity, which I covered earlier. But we have f of x is equal to x squared minus 4 divided by x minus 2 for x is not equal to 2 because it's undefined at x is equal to 2. So if we have limit as x approaches 2 from the left, limit as x approaches 2 from the right, and the limit from both sides on whether this two-sided limit exists or not. So if we have f of x is equal to x squared minus 4 divided by x minus 2, then what we're going to have, if it's x is not equal to 2, so we have x is less than 2 and x is greater than 2, and basically this is the function. And if we x this graph out, let's look over here. So if we approach from the right hand side as we get closer and closer to 2, as we get closer and closer, 2.1, it's 4.1. If we zoom in a lot more and go very close, it's approaching closer and closer to 4 as it's 4.03, and then 4.006, 4.004, 4.003 is the right hand side limit, so it's approaching 4. But if we approach from the right, it becomes closer and closer to 4 as well. 3.99, 3.998, 3.999. So the left and the right hand side both go to 4. That means the limit must exist. So let's check our answers. As it says over here, all of these answers are equal to 4. The limit from all sides and the given function is right at the bottom. Third example is an infinite limit. We are given 1 over x minus 3. We have to find from the left-hand side, from the right-hand side, and if the two-sided limit exists, and if it does, what is the two-sided limit? F of x is equal to 1 divided by x minus 3. And what we're trying to find is, as it approaches 2, 3, what is the limit either way? So if we zoom in on the area around 3 and scroll up, as you can see, if we're at 3.1, we're at like around 7. If we go up and up, if we zoom out a lot and then go a lot up, I mean like millions upon millions of up. But for us, we're only gonna go to about 1300. As you can see, it starts to become very close to 3. As you can see, it's almost on the line, but it's not quite there. So, as you can see, as the slope is going to infinity, it's a vertical line. So from the left-hand side, it's going to be positive infinity. Now, if we look at it from the right hand side and do the exact same thing, if we zoom out a lot and then go to around 1300 or 800 in this case, we're gonna find that it starts to go closer and closer to negative infinity, and the line is basically almost straight by the time it reaches 3. So the limit from the left hand side is positive infinity. The right hand side is positive infinity. The limit from the left hand side is negative infinity, and the limit from both sides doesn't exist, as the limits are not the same. If we check our answer, it doesn't exist, and as you can see with infinite limits, it doesn't exist. So to summarize these three examples, for whole discontinuities or removable discontinuities, the two-sided limit does exist. For infinite limits, both limits are infinities and the two-sided limit does not exist. And for jump discontinuity, both of the one-sided limits exist and are not infinite, but the two-sided limit does not exist. Now our fourth example will be limits at infinity. If we're given this function x of x is equal to 2x plus 1 divided by x plus 1. Now we need to find from to infinity and to negative infinity, and instead of a two-sided limit, we need to find what is the horizontal asymptote. So if we basically find it over here, this means that we have a purple graph. If we go back to home, this becomes another one of those graphs, except it's a bit different. So what we're trying to find is, as it approaches infinity, what the value is going to be. So if we zoom out a bunch to about a decent, 90,000, it gets very, very, very close to 2 as we go up and up in value, it being 1.999999, and as it approaches infinity, it becomes 2. Now, if we go to the left, if we do the same thing, except we zoom out to about negative, 600,000, or 490,000, or 500,000, it's so close to 2 that it basically becomes 2, but it is not 2, as if we substitute this value, it will be just a bit off from 2. So as it approaches negative infinity, it also equals 2. So both of the one-sided limits are equal to 2, and the horizontal asymptote as a result. Here's the limit at infinity question, and this is the solution. So we have values equal to 2 for the right-hand side. From the left-hand side, or the limit as approaches negative infinity, it's also 2, and the horizontal asymptote is 2, meaning 2 is the answer to all of these questions. Now our final problem is for a continuous function. If we are given f of x is equal to x squared minus 3x plus 2, we need to find the two one-sided limits and the function at x equal to 1, and also if f of x is continuous at x is equal to 1. Now, I'm assuming you probably found the answer to the last one already, as since it literally says continuous function in the problem, you would most likely figure out that it's continuous, but I'll go over it anyways to show you how it exactly is. So, if we have f of x is equal to x squared plus 3x minus 2, as you can see, we have a simple quadratic. So what we have to do here is we have to be like, alright, if we're approaching this as x is equal to 1 from the left-hand side, that means we have to start from less than 1. So 1 is around over here. So if we approach it from 2, then it starts to go closer and closer to 0. And if you want a little more proof, we can zoom in to about 0.80. And as you can see, it's very close to 2, only off by 0.01. So that proves that it goes to 2 from the left-hand side. From the right-hand side, if we approach 2, it gets pretty low at negative 0.25, but it increases until we're very, very close to 1, and in the end, it actually becomes 1. Now, if you didn't notice, 1 comma 0 was actually one of the roots of this quadratic function. Not very necessary to know, but just a nice thing that you might have not noticed, or you might have noticed. Since both one-sided limits are at 1, that means it's 0, and the function at 1, since it's continuous, is also 0. Now, it is continuous because it approaches 1 from both sides, and the function is defined at x is equal to 1. And here is the solution to this problem. Yes, it's continuous, limit exists and equals the function value. And these are all the answers to the question. So, thank you so much. See you in the next one. And thank you for listening and watching wherever you are in the world. Of course, if you have any more suggestions like this one or content ideas that you want me to make, please make sure to go down in the comments. It really helps me out a ton, and I can make a better experience for all of you guys. And it would really be helpful if you guys would like, subscribe, and hit that notification button for more awesome videos and more updates just like this. So, see you in the next one.